we want to make sure we understand in probability the difference between something that's mutually exclusive and something that's independent. If two things are mutually exclusive, otherwise known as disjoint, then if you saw a Venn diagram, they would have no intersection. People are either juniors or sophomores, but they're not both. So that's mutually exclusive. Now, if things are independent events, like juniors and males, there has to be an intersection, and the intersection has to be proportional to what's happening in the overall population. So let me explain. Like right here, you can see, for example, that of the juniors, half are female and half are male. And for the sophomores, half are female and half are male. So that makes these two events, the graduating class and the gender, it makes them independent because it doesn't matter which graduating class you're in, it's still a 50-50 split between the males and the females, and vice versa. In the junior class, of the females, 60 out of 100 are in the junior class, and of the males, 60 out of 100 are in the junior class. So there's got to be proportionality if there's going to be independent events. And so we need a test for whether events are independent or not. And the test is that the probability of event A happening should still be equal to the probability of A happening knowing that B has occurred. So for example, if we take a look and we say, all right, what is the probability of getting a female given that the person we select is a junior? Well, if we shrink the sample space down to just the juniors, then out of the juniors there's 120 of them, and out of the 120 juniors, 60 are females. So 60 out of 120 is 0.5. There's a 0.5 chance, a 50% chance of selecting a female given that the person we selected is in the junior class. Now, if these are independent events, then the conditional probability that we just calculated should still equal the original probability of getting a female. Well, what's the original probability of getting a female? There are 100 females and 100 males. So out of the 200 people in the class, the probability of getting a female is equal to 100 out of 200, so that is also 0.5. So these two events, gender and graduating class, are independent because it doesn't matter whether we know we selected a junior or not, the probability of selecting a female is still 50%. Now that works this other way too. We could say, well, what's the probability of getting a junior given that we randomly selected a male? If we looked at that conditional probability, what's probably get a junior given that we selected a male? Well, out of the males, there's a total of 100, and the juniors, that's 60 out of 100. So this would be a 60 out of 100 chance, which is 0.6. If these two events are independent, then it should be true that this probability equals the original probability of selecting a junior. And so if we look at it all together, there's 100 people here and 100 people there, so that's a total of 200. The juniors, there's 60 plus 60, there's 120 juniors altogether. So what's the probability we select a junior? Well, there's 120 juniors out of 200, and by golly, that's also equal to 0.6. So the probability of getting a junior is the same as the probability of getting a junior knowing that you've selected a male. That's how you test for independence. If we look at this, are events M and T independent of each other? Well, if they're independent, then it should be, for example, we could pick, well, what's the probability of getting something that's in M? Well, altogether that's 0.5. M is made up of two regions, so that would be 0.5. If these events are independent, then it should be true that the probability of M, given that T has occurred, is still equal to 0.5. Well, let's shrink the sample space down, or let's use our formula. Let's use our formula where we find the intersection of the two events, and that would be the 0.2. So put the 0.2 there, and then divide it by the probability of what's given, which is T, and that would be altogether 0.3. So we see that the probability of M occurring, given that T has occurred, is 2/3, and that's 0.667 or whatever. So the conditional probability does not equal the initial probability of being in M, so these two events are not independent. They would be dependent events. And we could say, well, if they're not independent, does that make them mutually exclusive? Are these two events mutually exclusive? The answer is no, because they have an intersection. For these two events to be mutually exclusive, they'd have to have no intersection whatsoever. In other words, the intersection would have to be empty. Empty. That's funny stuff right there. Okay, and now let's look at this. Are the events graduating class and driver's license independent from each other? So you can see that we randomly selected a bunch of juniors. 12 of them did not have a driver's license yet. A bunch of them did. A couple had their license revoked. These guys like to tease these guys over here and say, hey, not having a driver's license, that's kind of pointless, isn't it? Oh wait, you're not pointless, that's why you got it revoked. So whatever, they can, so here we go. What we're going to look at is how do we show or determine whether or not these events are independent? Well, all we have to do is pick out one conditional probability and one actual probability. I'm going to focus on this because these guys add up to 30. That's a nice total right there. So I'm going to use that. I'm going to say, okay, let me shrink the sample space down to the people that do not have a driver's license. So let's see, what's the probability we get, let's say this time a senior, given that a person does not have their driver's license? If we look at that conditional probability right there, that would be that would be 80 seniors out of 30. Remember, when we shrink the sample space, do the conditional probability, we can shrink it down to just this group right here with no driver's license. So that's a total of 30 people. And out of those 30 people, the probability that we have a senior, well, that's 18 out of 30. So 18 out of 30 is going to be 3 out of 5, so this is going to be 0.6. So that conditional probability is 0.6. Now, if these are independent events, then it should be true that the initial probability of getting a senior is also 0.6. Well, if we add these up, we have 18 plus 150 is 168, plus this is 174. We have 174 people here. We have 12, 74, 76 people here. So we have a total of 250 people altogether. So what's the probability we get a senior? Well, the probability we get a senior is 174 out of 250. So if we multiply that out, that should be 0.696. And so that is not the same as the 0.6. So because those two probabilities are not equal, then that tells us that these two events are not independent of each other. There's a dependency here. They're not mutually exclusive, but they're just not independent. So that's how we keep the two things straight and how we test for independence.